quantum mechanics does not exist.
Hi, my name is Manuel, and I'm going to present my research project proposal about quantum mechanics.
There are many misconceptions about quantum mechanics. To clarify, quantum mechanics is fundamentally a theory of linear operators acting on an underlying Hilbert space. A Hilbert space is a mathematical construct that behaves similarly to Euclidean spaces, allowing algebraic operations to be performed on its elements. These elements describe the states of a quantum system. It is crucial to understand that quantum theory itself does not exist in the physical realm. Rather, it is a model of physical reality. For example, atoms physically exist, but the concept of atomic orbitals does not. These orbitals are mathematical constructs. They serve as a basis set, much like the x, y, and z unit vectors in a 3D Euclidean space. One common misconception is imagining an atom as a system with electrons orbiting in fixed paths, like planets around the Sun. In reality, electrons exist in a probabilistic cloud, where their location is uncertain and can only be defined upon measurement. In theory, an infinite number of orbitals is required to fully describe an atom or molecule. For simple systems, such as the hydrogen molecule, the problem can be solved analytically due to symmetry simplifications. However, for many body systems containing more than 2 electrons, there is no exact solution to the Schrödinger equation. One of the most infamous concepts in chemistry is the periodic table of elements. Many of us have struggled to memorize the elements and their properties at some point. But memorization is not the goal. Instead, it is far more valuable to use the periodic table to model systems whose properties are still unknown. Let's consider the polyethylene molecule, one of the simplest polymers. For simplicity, we will focus only on its chain of carbon atoms. In periodic systems, the smallest repeating unit is called the unit cell. For polyethylene, this consists of 2 equivalent carbon atoms. According to the periodic table, the outermost orbitals of carbon are of s and p type. Using the geometry of the system, we can describe all possible interactions and overlaps between these orbitals. This process enables us to construct an approximate Hamiltonian that describes polyethylene. For small systems, these orbitals overlaps can be computed using assumptions like effective interactions or techniques such as machine learning. However, for larger systems, computational models become essential tools for achieving accurate predictions. Building on the principles of quantum mechanics and leveraging computational modeling, my research proposal focuses on advancing the design and understanding of metal organic frameworks, MOFs, for photocatalytic applications. Photocatalysis is a process in which light energy is harnessed to drive chemical reactions. This technology has gained significant attention for its potential in sustainable applications such as water splitting, carbon dioxide reduction, and environmental remediation. A key challenge in photocatalysis is identifying materials capable of efficiently absorbing light, separating electron-hole pairs, and maintaining stability under reaction conditions. MOFs have emerged as promising candidates in this field due to their modular structures, high surface areas, and tunable electronic and physical properties. MOFs consist of metal nodes coordinated with organic ligands, creating a porous, crystalline framework. Their unique architecture allows precise control over light absorption, charge transport, and chemical stability, making them ideal for photocatalytic applications. The objectives of this project are multiple. First, I aim to develop a computational screening method to analyze the electronic structure and photophysical properties of MOFs with high valence metal nodes. The goal is to identify materials with the highest potential for light absorption and efficient electron-hole pair separation. Second, the project will evaluate the thermal, chemical, and water stability of selected MOFs through high-performance simulations, establishing correlations between stability and the specific choice of metals and ligands. Third, I plan to create and validate computational descriptors that connect structure property relationships, enabling the efficient selection of materials with optimal features for photocatalysis. Finally, this project integrates a combinatorial approach, combining computational modeling with experimental data to accelerate the design of MOFs, significantly reducing both the cost and time involved in developing next-generation photocatalytic materials. Based on the exposed, it is hypothesized that combining in silico screening tools with the development of general structure property descriptors will enable the identification and design of MOFs with enhanced photocatalytic properties compared to conventional materials. This approach could optimize electronic conductivity, promote efficient charge separation, and ensure stability under specific operational conditions. Such advancements would position these MOFs as highly effective and sustainable materials for industrial-scale applications. More information can be found in the project proposal document.